All right, we're back. We're back. I brought myself a bit of water because my throat was getting really dry. Question number 4 now. We've got only 3 questions left, and I already know the last one, so yeah. And I know I know that Q5 is easy, and I know that Q6 is easy, so that's the last question that's gonna give me maybe a bit of a hard time. All right, so let's read this question. Hopefully you can see it. A strip of high-strength steel has a length of 0.3 meters and is 0.001 meter times 0.2 meters in cross-section. That's a bit too close. The steel's modulus of elasticity is 20 gigapascals and Poisson's ratio is 0.7. 0.27. It is subjected to an axial load of 15,000 newtons and is instrumented with 2 axially oriented strain gauges, each with R is equal to 120 ohms, and a gauge factor of S being dr over R divided by E, the axial strain, of 2.1. The 2 axial strain gauges are connected into opposite legs of a Wheatstone bridge R1 and R2 in the figure below. So, don't let the figure fool you. What's happening here is that we got the axial mounted strain gauge and we have 2 of them, right? And on R1 and R2, that means that they're actually acting with each other. As they expand, as the steel strips is strained, they're actually amplifying the result because they're on R1 and R3, right? All right, let's go. All right. The resistance of each of the 2 fixed resistors is also 120 ohm, and the power supply voltage is 2.5 volt. The bridge is adjusted to 0 voltage output before the load is applied. The full bridge equation is this. He gives us the full bridge equation. Praise Milarski. Find the output voltage of the bridge when the load is applied. Well, to know that, we'll have to know what the dr is. So we know that S, the strain gauge factor, is R is dr over R over EA. Steel's modulus of elasticity is 300 gigapascals and Poisson's ratio is 0.27. Right. So this is actually a bit awkward because I don't remember the equation for Young's modulus. It's stress versus strain. So I think it's stress over strain, and the modulus of elasticity will be 1 over that. So strain over stress, if I remember correctly. Now that's important because our stress is 15,000 newtons, because we know directly the stress. So our stress is 15,000 newton, and we have an equation for our strain. So we have 200 times 10 to the 9. Oh, and by the way, if someone get that's not very helpful if I don't know this. But can someone tell me what is the modulus of elasticity? What is it, strain over stress or stress over strain? I'll probably eventually realize it, but still. Is equal to, that's going to be equal to the EA that we're looking for over 15,000. Yeah, it's probably never mind that. I have a good idea what it is. 15,000 newtons over EA. Yeah, that's it. Let's use that divided by 200 E9. That gives us an EA of, well, usually strain is expressed in terms of microstrain. So I'll do times this. So 0.075 microstrain. All right. Now we know this, we know the S, so we know that it's 2.1. I'm going to erase this. 2.1 is equal to dr over r over the axial strain 0.075. Multiply this by 2.1. 0.1575 is equal to dr over r. Now we know that r is 120, so times 120 gives us 18.9 is equal to dr. That's a lot. 18.9 is equal to dr. I actually can't believe that. All right. Well, let's just assume it is correct for now. So our V out is the V supplied, which is 2.5 volt. 2.5 volt times R2. R2 is 120 times R3, 120, divided by R2, 120, plus R3, 120. Oh, never freaking mind. It's not well, yeah, it is 120. Plus 120 squared times. Now, dr2 and dr4 are 0. So we have 18.9 on 120 plus 18.9 on 120 because of the equation. So V out is 2.5 times 120 times 120 divided by 120 by 240 actually, 240 squared times 2 times 18.9 divided 120. So, wow. Nope, that doesn't sound right. If my equations are correct, it would be 0.2 volts, but that is just not correct. That shouldn't be. Oh, I see. Never mind. Yeah, I made a stupid mistake. But it's nice to know that your strain gauge is always going to have very, very small differences, because then you can see yourself, you see a big difference, you're like, wait, that doesn't work. And that's exactly what happened here, because I put the micro strains there. I didn't put -6. That's why it gave me such a high number. It shouldn't. That's not how this works. And there you go. Now I have a reasonable DR, which is 0. That's how many zeros? Oh, I'm just gonna put. It's my 18.9 again. But it's time to 1, 2, 3, 4, 5, 6. Times to -6. That makes sense. Oh, that's I don't trust that equation. That equation is really weird. I like my initial, like the equation from the manual, I like it better. Just this is some weird shit. Yeah. No. Oh yes, never mind. So the output is 19. Actually, let me put it this way. Times 1e6. It's 0.19 7. 0.0197. 0.0197 microvolts. That's the output. So that's A. Now B. If you were to install two strain gauges as R2 and R3 and have the two fixed resistors as R1 and R4, how would your measurement be affected? Justify your answer. Well, that's very easy, because when you look at the equation, you have everything that is the same except one very important part. It is that instead of having a plus between the two strain gauges, you'll have a minus between the two strain gauges. And I'll show you this new equation in a moment, but you will realize that it gives us kind of a bit of an issue. Right? Now this new equation is this. It's got 19.9 times 10 to minus 6 divided 120 minus 19.9 times 10 to minus 6 divided 120. Now what is that? That is 0, which means that V out is going to be 0, which is why you don't do that. And why is there a minus? Well, that's just directly from the equation, because R3 and R1 are working together, and R2 and R4 are always working against one another. That's the way the Wheatstone Bridge works. I see there is a few comments, so before going into number C, I will answer these comments. Strains times Young's modulus, that's basically strain times Young's modulus, that's basically what I did. You have to find stresses in FA, yep. You're saying FA? Are you saying I have to find strain? Force times area. Oh, it's true. You have to find stresses in force divided by area. That is correct. I am a dummy for not doing this. So the axial strain is going to be on the cut area. And so I will redo these calculations using this new input. Thank you very much. A is going to be 0.001 times 0.02. Is it that way? I'm pretty sure it is. Pretty sure it is. I hope it is. So that's the area, 0.00002. 50,000 divided that. So that's the thing, divided 200, E minus 9. Oops, nope. And that actually changes the results quite a lot. Stress is, yes, that's exactly what I calculated. Thank you very much. I made this mistake because I didn't consider the area. I just considered the force. I am sorry. So let's just do these calculations again. Times 120. Yes, all right. Then that will be all right. So the final output is actually 9.84 millivolts for A. B stays the same, and then C. If your measurements of strain are to be made in a variable temperature environment, describe the modifications you would make to your instrumentation with justification. All right, so to your instrumentation with justification. Variable temperature environments. So we know that R1 and R3 work together, and R2 and R4 work against. So what we would do is that we would put, if we assume that the transversely mounted strain gauge will not expand, and if it does expand, then we have to use a completely different piece of metal. Or we can just put it on the side. But the idea is to have a strain gauge that would work against the strain gauges we already have, which will get the temperature change, because we will subtract these changes from the initial So that is R2 and or R4 will become strain gauges that will be placed on the same metal at the same temperature but without the stress. Because if you get the equation, if we say that Vs R2 R3 divided by R2 plus R3 squared, if we say that that's become, I don't know, something called beta, then beta times, we'll have beta times an equation that is, if we get R3 to be a strain gauge and R2 to be a strain gauge, but R3 being placed on the metal that is being strained and R2 on the metal that is not being strained, then dr as delta R3 as two parts. That was the delta R strain and the delta R temperature divided by R minus delta R temperature, because the second strain gauge will have only the strain made by temperature. And of course, because they have the same initial R, they will cancel because it's exactly the same metal, exactly the same temperature. That means that it is going to expand in exactly the same manner. And so the RT cancels, and we are left with our strain only caused by the stress. That's how it goes. So V out is equal to beta times R. Well, I'll put stress instead because it's the strain gauge just measures strain, not stress, divided R. All right. D. The strip of high-strength steel is now instrumented with 4 of the same type of strain gauges, so i.e. same gauge factor. The two gauges that are axially oriented continue to correspond to R1 and R3, whereas the R2 and R4 are transversely oriented. In this arrangement, find the output of the bridge while applying the same load. Now, there is nothing being said about the capacity of the strain gauges to be able to how do I say this? There's nothing being said about the strain gauges to be able to feel not transverse, but perpendicular strains. So we'll assume that the strain gauges only experience strain in the direction they are parallel to them. That means that we need to find epsilon t, but that's where the fun comes in. If we go all the way back to our Q1, a short question number what was it? If we go back to our short question number short question number 8. We say that the Poisson's ratio is equal to the negative. So Poisson's ratio is equal to the negative of the transverse strain to the axial strain. And using that nice information, we can infer the transverse strain from the axial strain. We already know the axial strain. So we'll see that the transverse strain is equal to this. Times minus 0.27. Oh, divided by minus 0.24 times 0.7 times minus 1. All right. So it's minus 2025. It's minus 202 500 No, that's stress. What am I saying? That's stress. Whoops. No, it's just E minus 6. Because that's microstrain, and then you do times minus 0.27 times 1e6. So we get minus 1012.5 microstrain in the transverse direction. Now, we need to calculate dr for this. So we got our 2.1 equal to dr over r divided by et, and we'll get times 2.1. There's that, times 120. Get that our dr transverse is minus 0.255. Oh. So I'll show you, first of all, Poisson's ratio part here. And I didn't put the Poisson's ratio. I should actually put this before I put out the solutions. And then this new part, where we see it, we see the actual answer for the dr transverse. Now I'll just make sure that everyone understands where I come from. Saying 0.25 equals to this, what we're looking for, the transverse strain divided by 3750 times 10 to the minus 3750 times 10 to the minus 6 strain for the axial direction. Now we have both strains, we have both del r's. So using the equation provided to us by our Lord and Savior Milarski, we can find the V output. So our beta, as we stated earlier, is 0.625 times. So we have exactly the same setup as earlier. 0.945 is the dr in the axial direction. So that's divided 120 plus 0.945 divided 120 minus plus, because it's minus, so it's plus 0.255 divided 120 plus 0.255 divided 120. So that's what we get. here. I was just going out of the window just to know if I was showing correctly. And now we calculate the final answer. (0.945 divided by 120 plus 0.945 divided by 120 plus 0.225 divided 120 plus 0.225 divided 120 gives us a V out of 0.012, and that's a total of 12.32 millivolts. Is that higher than our first one? It should be. It is, slightly. Now, the question is why, oh why, is it not impeding? Because we've seen that the delta R, the change in R, is negative for the transversely mounted strain gauges compared to the axially mounted strain gauges. The reason why is how the Wheatstone bridge works. Because R1 and R3 are always going to work, and that's, by the way, the diagonals, are always going to work together, meaning that they will have the same sign. And R2 and R4 are going to work together and have the same sign, and both of those have opposite signs. So when we use the transversely mounted strain gauges on the sign that is opposite to what we were previously using, we're adding to our voltage. Now question E. Using the same strain gauge configuration as in D, an unknown axial load is applied to the strip of steel. Interesting. The resultant output voltage is 25 millivolts. What is the applied axial force? This one is a long one. First of all, we need to relate axial and transverse strain. So we have the Poisson's ratio 0.27 is equal to minus epsilon t divided by epsilon a. So 0.27 minus 0.27 epsilon a is equal to epsilon t. Now that we've related epsilon a to epsilon t, we can replace epsilon t by its relation with epsilon a later on. So 2.1 is equal to the dr axial divided by r divided by the axial strain, and 2.1 is also equal to dr transverse divided by r divided by the transverse strain. All right, so now we just relate these quantities together. So 2.1 epsilon a divided by, actually, it's going to be 2.1 epsilon AR is going to be equal to DRA, and 2.1 times minus 0.27 epsilon A times R is going to be equal to dr transverse. What does that do? It's 2.1 times minus 0.27. That's minus 0.567 EAR is dRT. Now, we take the Wheatstone bridge equation, and we already have V out. So we have 25 millivolts. That's 0.025. 0.025 is equal to 0.625 times our, first of all, it's the same configuration. So the A's are going to be for the positive ones. So 2.1 EAR divided by R, the R's cancel, plus 2.1 EA plus 0.562 EA plus 0.56, not 562, 567 EA. Well, not EA, epsilon A. You probably understand what I mean. So if we put all of this together, 2.1 plus 2.1 plus 0.2, 0.567 plus 0.567 times 0.265, you're gonna get that 0.025 is equal to 3.334 epsilon A. Like this. All right. Zero point 0.025 divided by 3.334. That'll give us an epsilon A of 0.0075. I'll show it on the camera a bit longer. You guys to understand. Try to understand. Now, these R's will cancel in every single one of these terms. I did not repeat the R's because they will cancel. And the R's are basically 120 because it's 120 here, 120 up, they cancel. And as such, we'll just have a string of epsilon A, and we got our answer for epsilon A here. Now, using the same method as earlier, we'll see that the 200 times 10 to the 9 is equal to the stress over the strain, in this case 0.0075, multiplied by 200 times 10 to the power 9. It gives us a very large number. And now we'll multiply this by the area, because the area is similar, where 0.00002, and that gives us a sigma, a F, a load of about 30 kilonewtons. And that's question 4. Q5 now. Question 5. Question 5. A pitot-static tube uses a manometer readout with a fluid having density of 820 kilograms per millimeter cubed. I'll just look at this here. Nothing bad's happening. So density of 820 kilograms per millimeter cubed. The tube is oriented parallel to an A stream at 1 atmosphere, 25 degrees Celsius, having a velocity of 30 meters per second. The accuracy of the dynamic pressure measurement is plus or minus 0.1 millimeter of the height of the nanotube. I don't care about this. It's going to be used later. Now, A. To first calculate A, we absolutely need to find the equation using Bernoulli's equation. All right? So I will derive it using Bernoulli's equation. Now, there's a couple things we assume here. So this is a pitot-static tube. One of the two velocities is 0. And then we assume that the Z will actually cancel itself because that's the same height. So these cancel, and this one is 0. Choose one of the two velocities, and then we'll express the rest as a function of the other. And as such, we got P1 minus P2 times 2 divided by the rho of air. Square root of all that is equal to V2. Like this. Now, the pressure difference is P1 minus P2. And our question is to calculate the pressure difference measured by the manometer. So, basically, we need the speed, we need the rho of air, And that's it, really. So the speed V2 is what? 30 meters per second. And that's nice. Now the rule of air, we actually have an equation for it given to us by our Lord and Savior Milarski, which is P, pressure, divided by the R of air, constant given to us by Milarski again, and T, where T is in Kelvin. Never forget it. So what that is pressure of 101.3 times 10 to the 3 pascals, because it's a 101.3 kilopascals, atmospheric pressure, and that's our initial variable. The temperature will be 273.15 plus 25, so 298.15 times the R of air, which is 287. 101.3 3. Oops. 101.3 divided this 298.15 divided 287. That's 1.18. So we have everything now, and we'll actually derive it in the other way around. So P1 minus P2 is 30 squared times 1.18 all divided by 2. And that gives us 531 pascals. Because we already all did everything in pascals, so we'll get pascals. Now B, express the fluid velocity as a function of this pressure difference and the thermal-physical properties of the air. What are the thermal-physical properties of the air? It's temperature, it's pressure, and it's R, it's gas constant. So basically, we take exactly what we've got earlier, so 2P1 minus P2, divided by, and we replace rho by P air, pressure of the air, divided by the R of the air times T of the air is going to be equal to V2. But that's basically it. That's our answer right there for for B. And C, calculate the uncertain. Okay. Now before I do C, and if anyone was in MECH 261, we're done now. You and your exam will get more questions than this, of course, but now it's only MECH 262, meaning it's just probability for now on, statistics, etc. And in Messenger, actually, someone gave a comment, a very interesting comment. What formulas will be given? Very, very important question, and one that our Lord and Savior Milarski decided not to answer. So that's great. That's a shot in the dark. Hopefully you guys find it. If you don't, well, too sad. Now, C, calculate the uncertainty in the measurement of the fluid velocity assuming a nominal value of 30 meters per second. All right. Measurement of the fluid velocity assuming a nominal value of 30 meters per second. The measurement of fluid velocity assuming nominal values of 30 meters per second. That would mean that so P1 minus P2 will become delta P. It will be a single variable delta P, right? Now, yeah, that's it's not according to me, Ramadan. That's actually what he said. I don't know if you're listening. You're probably not, but That's what he said. That's not me. That's him. So our P1 minus P2 will become delta P. Now we assume a nominal value of 30. This means that the values will be what happened at 30. So 1.18 for delta P. And dynamic pressure measurement is this of the height of the manometer fluid. The static pressure airstream can be assumed to be exact, but its static temperature has an uncertainty of 1.2 degrees per 1.2 degrees Celsius. So it says the accuracy of the dynamic pressure measurement is 0.1 millimeters of the height of the manometer. All right. Fluid. Dynamic pressure measurement 0.1 millimeter. So we have a dynamic pressure measurement and a static pressure measurement. Here, because we canceled P1, this means that our P2 is the dynamic pressure measurement. But with that said, the error is going to be the same, because if you have no pressure on P1, no error on P1, right? Omega delta P, actually, is equal to P1 minus P2. So you'll have your derivative in terms of P1, which is 1, times the error, which is 0, plus the derivative in terms of P2, which is minus 1, times its error, which is 0.1 millimeter, which is, this would talk in function of meters, 0.001. And, well, we have that the error of delta P is going to be just 1 times the error of P2. Oops. Something like this. So it's equal, basically. This pressure is this plus or minus 0.1 millimeter of the height of the manometer fluid. So now that's 0.1 millimeter of the manometer fluid. Ooh, yeah. So our delta P is going to be equal to the rho of the fluid times, actually it's not the rho of the fluid, is it not? It's the rho of the fluid minus, well, it compares to the, if we assume that it compares to the rho of the air, it's minus rho air times G times delta Y, right? And there's the delta Y we know the thing with about. So the whole thing, the first part was just to prove that in looking at the delta P, we're not making a mistake. And that's exactly what we're going to do. So now this is the error on the density. Now the error on density is about 0. So we can say it's pretty much a constant. So we're gonna have well, there's this 0. This is a constant. It is a constant. So we'll just do our 820, which is the density of the fluid used in the manometer, minus the density of the air, which is 1.18. times 9.81, because we are using the SI system. That's 1,332.6 times delta Y. It's a very straightforward thing. Wait a second. Yes, okay. It's a very straightforward thing. And now we'll just find the incertitude, which is going to be equal to this times the incertitude of the delta y, which is very small. So, and delta p is in pascals, so we got 8,032.6 times delta y times the uncertainty of delta y, because that is a derivative of delta y. Omega y. And what happens next is that we do times 0.1 divided 1,000, 0.0001, and times 8032.6. That gives us an error of 0.8 pascals, plus or minus. Now, I have omitted the square root. I have omitted the squares because we have only one variable. So its derivative times the incertitude of that variable is going to be all that we need. That's the incertitude of the pressure measurement. Now, we must find the incertitude of the velocity. Let's find the incertitude of the velocity, and we will try and find a new way of representing the formula, because it's getting a bit complex. So 2 times delta p times r air times t air divided by P air, which we assume is constant, is V2. So that's that. Now we need to find del V2 over del P, which is going to be 1 over this huge freaking thing, 1 over 2 times this 2 delta P times R air times T air times P air times R times the derivative of the inside, which is 2R air times T air divided by P air times the uncertainty of P. Well, times the uncertainty of P, we'll see that later. For now, since these are all constants, we'll actually calculate what it means, what this constant is. 2 times the delta P. Delta P was measured previously to be, in this case, at 531, times the rho of the air, which is 287, times, not the rho of the air, the R of the air, times the temperature of the air, which is assumed, which at this point is 298.15 Kelvin, divided by the pressure of the air, 101.3 times 0.383 pascals. Take the square root of that, times 2, 1 over this. So you got 0.017 times 2 times 287 times 298.15 divided by pressure of the air, 101.383. That's 1.69, 0.0117. So that's a total of 0.029. The derivative is worth 0.029. This whole thing boils down to this, really. Now we need to find the derivative of V2 with respect to T, which is going to be exactly the same first term. 2 delta P times R air times T air times divided by P air times 2 delta P R air divided by P air. And that's 0.017, like we've seen again. And that's 2 times our 531, like we had before, times 287, divided by the pressure of the air, 101.3 E3, which is 3. That gives us, for this derivative, 0.05. So again, this entire thing goes on to that number. And as we've seen in error propagation, the error on V is going to be, the square of the error on V is going to be equal to the square of the derivative of each variable times its respective error. So for the pressure of 0.029 times 0.8, that's squared, plus 0.05 times 1.2 degrees Celsius. Now, that's important because 1.2 degrees Celsius is the same as 1.2 degrees Kelvin, plus or when you consider plus or minus. 1.2 degrees Celsius is going to be 274.35 Kelvin, but plus 1.2 degrees Celsius is the same as plus 1.2 degrees Kelvin. That's important to understand for this particular part. So 0.029 times 0.8 squared plus 0.05 times 1.2 squared. Take the square root of this result, and we'd find that the error on the spin, the omega V2, is 0.06 meters per second, plus or minus 0.06 meters per second. That is C for this question. Now D, which of the two sources of error is the dominant one? That's an easy question to answer. It depends, is which one of them is the largest one. And obviously, it is going to be temperature, because one, I'll show this, right? But one, if this is correct, then it is temperature, because one, the derivative of the pressure is smaller than the derivative of the temperature. Also, the error on temperature is larger than the error on pressure. So it has to be temperature, which is a dominant error. Is the dominant error. And that's question 5 done. I see. Alien looking like formulas. I like that saying. All right. Now it's down to the last final question, Q6. Now, I won't lie, I've already done Q6 once. So I'll do it with you. And we'll have fun together. Now, Q6 is a bit strange. I'll do A verbally. A says, describe the different approaches to use in calculation of confidence interval for the mean value of a random variable when 1. The random variable has a normal distribution and a large sample size can be obtained. Now this is the easiest case because it has already a normal distribution and a large sample size can be obtained. That means that we just use the normal distribution, and the formula to get a confidence interval, you have to know this, is Z, your Z from your normal distribution, times your sample, the root of your sample variance divided by the root of n. And that's how you get it. That's how you get it. You use z as seen, well, not as seen, but as calculated using a normal distribution table. All right. 2. The random variable has an arbitrary distribution, and a large sample size can be obtained. All right. Now this one, we have that for sufficiently large n, right? For sufficiently large n, we will obtain a normal distribution, which means that we can still use the exact same way, the exact same thing. So same as number 1, as I. If I'm correct, you can use the exact same thing if your x is not normally distributed, because for large enough n, it will become normally distributed. Now 3 is different. The random variable is a normal distribution, all right, and only a small sample size can be obtained. In that case, you have to use the other distribution we've seen, the t distribution, and the formula is slightly different. You have t, which is a function of the, I don't know how they call it, of the percentage you want, and n minus 1, the degrees of freedom, and you multiply that by the same thing. So you just have your t distribution is going to be different than your s distribution, but essentially it means about the same thing. So now question B. Experiments were performed that examined the load at failure of 11 specimens, and I will show you this. Of 11 specimens, of a certain alloy. The results were as follows. Calculate the 95% confidence interval for the mean load at failure, assuming its distribution is normal. The table of the area under the student's t distribution is given on the next page. All right. Now, we already know how to find confidence intervals. We take the area for the t distribution times our sample, the root of our sample variance, divided by the root of the number of sample we have. Now, the sample variance is obtained by summing every single one of is obtained by summing the sample value x minus the sample mean, that we'll call x bar, the square of that. So we obtain this by doing this, but that's not all. Once we've summed everything, we have to divide by n minus 1, where n is the number of samples we have. So to repeat, our sample, the root of our sample variance, the submean variance is obtained by summing every single one of the difference of the sample to the sample mean squared and dividing the whole thing by n minus 1. So that means we need the sample mean. The sample mean is obtained by summing every single sample and then dividing it by the number of samples. Now this is actually fairly easy. We know we have 11 specimens. We'll just sum everything. So 19.8 plus 15.4 plus 11.4 plus 19.5 plus 10.1 plus 18.5 plus 14.1 plus 8.8 plus 14.9 plus 7.9 plus 17.6 divided by 11. We obtain 14.36. That is or sample mean. Now the sample variance is going to be much longer to calculate because it's ever so slightly more annoying to calculate because it's much longer. So calculate the terms one by one, and then we sum them all together. 15.4 minus 14.36 squared is 1.08 plus 11.4 minus 14.36 squared is 8.76 plus 18.5, no, that's, we're 19.5 minus 14.36 squared is 26.42. 10.1 minus 14.36 squared is 18.15. Now we add 18.5 minus 14.36, we square it. 17.14 plus 14.1 minus 14.36 squared is 0.07 plus, oh, I won't have enough place, man, it's really long. So 8.8 minus 14.36 squared is 30.9 plus 14.9 minus 14.36 squared is 0.3 plus 7.9 minus 14.36, so we square this. This is 41.7 plus 17.6 minus 14.36 squared, 10.5. Now we sum everything. 41.7 plus 0.3 plus 30.9 plus 0.07 plus 17.14 plus 18.15 plus 26.42 plus 8.76 plus 1.01 plus 29.59. And we divide it all by 10, which gives us a variance of 18.46. And the root of this variance is 4.3. Right. Now that we've obtained this, we can actually go look on our t-distribution. Here. Can look on our t-distribution. We know we have 10 degrees of freedom. We want a 95% interval. So we're going to take the middle one because 0.25 times 2 is 0.05. 0.025 times 2 is 0.05. So we'll take the middle one, and that corresponds to 2.228. So take this. So 2.228 times the sample, the root of the sample variance we calculated, which is 4.3, times square root of 11, will give us square root of 11 times 2.228 will give us 2.89. So calculate a 95% confidence interval for the mean load at failure, which means that we have the confidence interval, we have the mean, which is 14.36 plus or minus 2.89. And that's loads in megapascals. So we'll have this in megapascals too. All right. Now, C. All right, now C is a slightly more complicated one because we need several different things, and it's C is just slightly long, and you already have everything, right? You know that you need A times T plus B. You got a formula for A, you got a formula for B, and you got a formula for R2. You know you need the formula. You know you need that these parts. You need A, B, and R squared, and you need to assemble them in the exact same way it tells you. So at this point, you've pretty much finished the exam, and you're taking it slow or very fast if you act like me and you're trying to explain several people at the same time. Although I don't think I've done an excellent job at it. I've done my best, I guess. And well, that's it. So we'll just, it's gonna be very boring from now on, but we'll just calculate this. So I'll just do it. So A is, N is 5. So for these guys to be faster, what you want is already have everything there. So N is what? N is 5. The sum of xi, yi is what? You need to calculate this. So it's 290 times 98 plus 300 times 100 plus 310 times 107 plus 320 times 320 times 108 plus 330 times 115. So that's 164,100. Now the sum of the xi's is, and x here is t, so 290 plus 300 plus 310 plus 320 plus 330 is 1250. The sum of y is 98 plus 100 plus 107 plus 108 plus 115, which is 528. Now, is there anything else you need? Yes, you need the sum of x when x is squared. So 290 squared plus 300 squared plus 310 squared plus 320 squared plus 330 squared, which is 481,500. So, once you've got all this, you're almost ready. All you need, the last thing you're going to need is the mean of y. And the mean of y is the sum of all y's, 528, divided by the number of y's, which is 5. So that gives us 105.6. Now that we've got everything, you calculate A. It's called 5 times 164,100 minus 1,250 times 528, everything divided by 5 times 481,500 minus 1,250 squared. You just calculate this very easily. This, use parentheses. Don't forget to actually do these calculations correctly, because that can hurt a lot in an exam. That gives you 0.19 as A. Is that correct? 9 times 164, 100. 60500 divided by 5 times this big number minus 1 squared. 160,500 divided by the answer. Yeah. So A is 0.19. B is what? B is our 481,500 times 528 minus 1,250 times 164,100 divided by exactly the same thing we had on top. I mean, when we calculated A. So 500 times 528 minus 1,250 times 164,100, not 400, 100, divided by 5 times 481,500 minus 1,250 squared, and that's 58.1. I think that is correct. Just verifying, making sure. Yeah. Yeah, so 58.1. Now, we need to a new term, which is going to be the sum of AXI's plus B minus YI's. All that squared, and that's just... I mean, at this point, I think I'm gonna stop. There's 3 people watching. It's just very, 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 very long, and it's just computations at this point. They already give you everything. So yeah, thank you for listening, and I hope it helped. Goodbye.